We had this on Monday already, where I gave you a bit of an intuition on how to understand the principle behind large deviation theory, and in particular sample path large deviation. Then I wanted to expand a bit on that. This is lecture 3, large deviations. So the first concept that I wanted to introduce is dominating point. This is a rather intuitive concept. Imagine x to be some Gaussian random variable. Maybe in RD. Maybe x is distributed according to a normal distribution centered at 0 and with unit covariance in RD, which is like a d-dimensional identity. And I again have an observable, how I called it the other day. Which is merely a function from our random variables, maybe into the reals. You can have maybe multiple observables that are of interest to you, but in the end, this is the quantity that we care about. For the rogue wave example, this would be the height of the largest wave. For maybe some cloud example, this would be the mean temperature over a region or something like that. And these functions f can be rather complicated. I'm here in a simple setup because x is just an RD in Gaussian. Then the extreme event probability that we were always looking at, just to remind you, is what I call P of z. It's the probability that the function, our observable of the random variable, exceeds some threshold z. And we also have the property that for the set AZ being all those realizations for which the threshold is exceeded, you can basically write P of z as an expectation of the indicator. That's maybe just a way of writing it. So I'm counting always as a yes if I hit the set of extreme events and as a no if I don't, and then I average. That's, of course, a way to compute this. So we can look at this situation and interpret it geometrically. If I have a Gaussian random variable with unit covariance, let's say this board is RD, this is the origin, then isolevels of probability look like circles, right? This is the most likely point because it's at the origin, and then the further the distance from the origin, the less likely these points become. If you wouldn't have a unity covariance, then this would be maybe ellipsoids, and if we would have a non-Gaussian distribution, maybe this would be a much more complicated function. But for now, let's just restrict ourselves to this case. And then we have these sets, AZ. These are isolevel sets of the function f, which may be complicated. Probably, if we are strict about it, we need to have some kind of guarantees about like differentiability and extremal points and so on. But let's just say this is AZ. Basically, what I'm saying is the function f is defined everywhere, but in this region, the common region, it's below z, and only in this region is above z. And I already highlighted it a bit to show that clearly, if I now go ahead and do these kinds of rejection sampling algorithms, as we did with the coins, or as I did with Brownian motion, most often I will hit close to here, and I'll throw them away in my naive Monte Carlo. Sometimes I hit AZ. But whenever I hit AZ, I would probably hit it somewhere close to here. only very rarely outside, maybe one here, but most of them will be located at that. This is simply because these are the points that at the same time are in the set that I'm interested in, so I'm not throwing them away or weighting them with a weight of 0, but still relatively likely in comparison. So in a very abstracted way, and in a very rough notion, all that large deviation theory is saying is that there is this point, the most likely point in AZ, which we can use as a placeholder for all the others. We don't sample anymore. We say the probability of hitting AZ at all can be, at least in its scaling, replaced with this point alone. So this point, which we call X star maybe, is called the dominating point. The reality, which we will not go into really deeply here, is not that this point can replace all others per se, but more like as I let go z to infinity and this set recedes away from the origin, the scaling of probability of this point is the same as the scaling of probability of the whole set. So the thing that I'm missing if I replace the whole integral with just a point is some kind of normalization factor. But usually I don't care. If I'm just here to compare probabilities, how much more or less likely something becomes as I change z, this is enough. So the idea to say X star, the dominating point here, is the only thing relevant, is to say P of z, written as this, we can say is simply the integral of AZ over our density. And if I say, just for ease of notation, maybe rho of x, our density, if it would be Gaussian, has a specific form, but in general, I can say this is maybe proportional to something like that. So if rho is the normal distribution, then I of x is x squared over 2. So sum over all I in Rd, I squared. But in general, whatever my density is, I can look into the exponent. Then what I can say is that I can replace this integral over all of AZ in proportionality, not in exact notion, by e to the minus I at x star only. So that's written in formula, what I was saying in words. Sorry, I have to start. Is that I'm only interested at the dominating point itself, and I'm evaluating this one, this density only at that point, and I neglect all the others. So this is not true inequality, as I said, but there is a constant in front of this that makes this true in the limit. In a sense, this is the whole idea, but let me write down what exactly I mean with x star, because so far it's only in the sketch. X star is the R min of I of x over AZ. So that's in formula what I was saying in words. It's the point of minimal I, where I, in the case of the Gaussian, is simply the distance to the origin. The factor 1/2 obviously doesn't matter for the optimization problem. So I'm saying I have some kind of log likelihood in the exponent, and the minus makes this a minimum instead of a maximum. But this is the point of maximal likelihood or of minimal distance to the origin in the Gaussian. This is the dominating point. Is that so far so believable? I understand that this is not a derivation, but maybe this picture makes it somewhat intuitive that instead of sampling a lot and throwing away a lot, this is the point that I could at least in principle compute instead by solving this optimization. Maybe another thing to note is what we did on Tuesday, which was importance sampling, basically amounts to shifting this distribution to be centered on that point. And a good change of measure in our importance sampler would be one that shifts the mean from here more closely to that set, where you are rejecting far less of it. Which maybe also hints at, but we're not going to discuss that at all, to use the dominating point as an optimal tilt for your importance, which can be done. All right, maybe one thing to note, this is obviously a much simpler case than anything that we can do with sample path, which I want to get to. This is just a real valued or vector valued random variable that's also Gaussian distributed, but this can already be very complicated. So note that f for example, the space from which we are drawing random numbers, Rd in our case, could define initial conditions of a partial differential equation of some complicated atmospheric model maybe. And then F takes this initial condition and integrates the PDE forward. And then finally evaluates something on the final configuration. And whatever, right? Why am I naming this example specifically? Because this is exactly the example that I showed on Monday with the rogue waves. This was this simple case. The initial condition was drawn from an empirically determined measure of ocean surface distribution, which basically said this is how the energy is distributed across certain wavelengths in the ocean. But this is a Gaussian distribution. It's finite dimensional because we only have by numerical necessity, a finite number of wave modes in our domain. Each of them has a variance. So the only thing that we are drawing is the Gaussian distributed random number in Rd, and d is not even that big. This gives us some wave field that then gets pushed forward by some nonlinear wave equation. On the final time, we're looking at the maximum elevation of the sea surface, and all of this chain of things is our function f. And at the end, the only thing that comes out is a single number, namely the height of the wave, but f itself contains building an initial condition out of an Rd vector, integrating a PDE forward, and then evaluating the final condition. Which of course means that these sets might look rather complicated, and for example, if the PDE would be chaotic, probably you wouldn't have like a single nice point and the whole procedure would fail, so it's not guaranteed to work. But if you have certain regularity guarantees, this is exactly still contained within this case. So even though this looks like we're just going from something finite dimensional to something finite dimensional, in between this can be very complicated. You can of course also imagine, I don't know how much experience you have in numerical optimization, but in order to compute the minimum of a function, you probably need its gradient in order to descend by whatever method you're taking. And the gradient of I must somehow, and the constraint with AZ must somehow include the gradient of f. So you will, for these complicated examples, compute gradients of PDEs, so you need to do with kind of adjoint methods and forward backwards sweeps and so on. We're not going to do that, but I'm just saying even this rather intuitive picture is already applicable to rather complicated examples. Write down that. This is the rogue wave example. and many others. Are there any questions so far? Okay, so the next thing that I wanted to get to is, and maybe there's a pattern here, to apply this in infinite dimensional spaces. That means to apply this to sample paths of stochastic differential equations. So this is called sample path large deviations. Also, right inventor theory. It's a bit hard to Google because it's Russian and Latinization is a bit matter of interpretation. So you see this as well, and sometimes two L's. So what is the generalization that I want to do here from this situation is that we are not drawing a d-dimensional random number, that's Gaussian, but instead a Brownian motion. And as I hinted at on Monday as well, some random walk basically corresponds to a Gaussian increment at every instance in time. So infinitely many of these random dimensions, but still Gaussian. So in some sense, still a sphere, just an dimensional sphere. It's a bit awkward. And then you again have this F. So some things become simpler, some things become more complicated. This space becomes much bigger, but usually the function F becomes much simpler. So I consider some sample path t from 0 to t, and x is supposed, so xt for every t is supposed to be in Rd. So this is now a d-dimensional random trajectory instead of a d-dimensional vector. Solution to the SDEs that we had all the time. I have some deterministic part of my dynamics, and I have a white in time Gaussian Brownian motion added as noise, which you can generalize later, but that's just the simplest case. So as I said in words, let me just write it down. Intuitively, we are in the same situation by drawing a Gaussian random variable each instance in time. Where I would say, if you write it like this, x naught is b of x plus eta, and eta is our white noise, then you would say eta is distributed according to, again, an exponential, and then here we have minus 1/2, and instead of a large sum, we have a time integer. So you could call this the I of x from before. That's the analogy. Instead of having a finite sum, we have an infinite sum, we just call it an integral, right? That this is true is maybe non-trivial mathematically, but intuitively I think it's rather clear, right? Each of these actually might be debated out. Because I had d omega and now I divide by et.
Tobias, in computational optimization, wouldn't this be called pivoting, this I of n that you're using?
I'm not sure. Pivoting in optimization, what would that be?
Well, that's exactly what you do as well. Well, actually, that's idea is similar. So you choose one of the paths that gives you most likelihood to sample the trajectory that will get you to the minimum. It reminds me of that. Maybe it is not exactly that, but that's thinking.
So this is not this is not a thing you do in optimization. You mean it's a thing that you do in sampling?
Yeah, maybe I'm
I mean, this is optimization. Clearly, we are optimizing a function.
Yeah, maybe okay.
Yeah. So if we are in this situation that has now disappeared behind the board, we can then again say something about probabilities of observing a certain path and deduce from that limiting probabilities of observing certain events, maybe at the endpoint of these paths. So what we get is something that looks like the following. The probability, let me write it down, but it's a bit more lengthy, of our sample path being close to a given path so I'll say this in words now. The supremum over time just means what's the maximum assumed value of the argument. And the argument is just the difference between our solution of the SDE, a completely drawn sample, and the path of my choosing. So what's written here is that if this supremum is bounded by delta, this means that I stay within a delta tube of a given path phi. I give myself some realization or some continuous path in my configuration space in RD, and I'm asking what's the likelihood that I stay within delta around it. This probability in the limit epsilon to 0 is proportional to an exponential again, where in the exponent I have the smallest parameter to the -1, and then this rate function. And this rate function can be explicitly written down, and I hinted at what this is. So this is what I called I earlier in the simpler example, in the simpler case. It's called the rate function. That's what a large deviation theorist would call it, or an action. This is what a physicist would call it, coming from the path integral arguments that we did on Monday. But it amounts to the same thing. And it is given by the integral of a function that I call the Lagrangian. If this is well defined and finite, and otherwise just infinity. So infinity for S means the probability of 0 formally. So whenever this isn't even defined, then these paths can't happen. But if this is well-defined quantity, then this gives you the limiting scaling of the probability. And I need to give you the Lagrangian itself. One half, and then phi dot minus b of phi. So we had this argument on Monday on why this is true. So it shouldn't be a dot here. Where did I add the dot? It was on the other board. Time integral is over eta of eta. Why is this intuitive? The only thing I'm saying is that in the finite dimensional example, we had I of x to be proportional, sorry, to be equal to 1/2 sum over I from 1 to d xi squared. Now we have our larger function s of eta to be 1/2 time integral from 0 to t beta squared dt. I mean, I'm just arguing by analogy here, but that gives you the right hint. And then, because we have x dot equals b of x plus eta, we have eta is equal to x dot minus b of x, which means that s of eta, sorry, s of phi now should be exactly that. So intuitively, what's happening here is that our equation says x behaves like b, except there is some small fluctuations that scale with epsilon. So whenever my x doesn't behave like b, the difference is must come from the noise, and I know for every noise realization how likely it is. It's this likely. So I can instead express this in the trajectory itself. Yes.
Can you elaborate on what's on top? So it says epsilon to infinity.
Sorry, epsilon to 0.
Okay.
But not sure whether this was your question.
Yeah, or maybe it's also already. My thing was that the S of phi is either finite or infinity.
Well, the infinity case is just for like mathematical reasons. Every phi that you would usually evaluate falls into this class. So these are always finite values.
But if you take limit epsilon to 0, for example,
yes,
in the case that that S is finite,
yes,
then it would just be
0,
right?
And that's indeed the case. So this is the intuition behind that epsilon to 0 basically corresponds to this receding to infinity, or maybe because epsilon defines the probability, maybe these circles receding to 0, these events become less and less likely, clearly. All of them exponentially so. The only exception is when S itself is 0, then probability is 1. But if S itself is 0, I am with this set including that point. So then even if I recede to this point, I will still have a likelihood of 1. But yeah, it's a good question. Maybe this I should have expanded on. We are always in this. I mean, here I'm making the argument on this is some more intuitive coming from the SDE, but these probability limits always are true only in the epsilon to 0 limit, because above that, these points that don't quite hit also contribute. It's only if we let this become arbitrarily small is that only this single point will survive, because all others are even less likely in this scale. So that's maybe the next point to make also in writing down. This was saying that the probability of staying within a delta tube around any phi that I want exponentially decays. So if I'm now asking for a concrete Venn event, the probability that f at the final point exceeds some threshold, in principle, I would need to add up over all of these for every phi. Every phi that hits my threshold has a scaling of probability like this. So the probability of drawing a sample path that's close to that phi exponentially decays. All of them very quickly exponentially decay. So the one that will remain in the end is the one that has minimal s. I have infinitely many phi that connect my starting point that I'm given to the outcome that my threshold is exceeded. All of their probabilities have a very strong decay in the limit of epsilon to 0. So the one that will dominate them all is the one that decays least quickly, which is the one that has smallest s. So this will also scale like this. but instead of S at phi, it's the minimum over all phi in some more complicated set, maybe I call it like that. Where this set is now the set of trajectories which have phi at 0 being our starting point and f of phi at the end point exceeding the threshold. So this is now a set of trajectories, and I minimize over all possible trajectories that will exceed the threshold the action, and the action evaluated at that will have the right scaling because all others are basically have already decayed to 0 much more quickly, exponentially more quickly. In particular, there is a trajectory phi star, which is maybe then the argmin of the phi in this set. Such that our probability basically scales like e to the minus epsilon to the minus 1 s at phi star. This corresponds to the dominating point in the finite dimensional case. We have a dominating trajectory in the infinite dimensional. This phi star is called the maximum likelihood path or the instanton. Maximum likelihood path is possibly misleading because these are paths of exponentially low probability. They maximize the likelihood of all paths that realize a red event. Therefore, it's a maximum likelihood path, but it is an unlikely path. Instanton is maybe nicer because it sounds very mysterious and you don't have any intuition of what it means, except if you come from quantum field theory, where this has a very clear meaning, namely that it is the minimizer of the action, which is the case here as well, which is where the name comes from. So in quantum mechanics, you would have a very similar construction where you would need to sum over all possible paths. You have the smallest parameter, in that case, h bar. So you're not really in a limit, h bar is just given, but h bar is very small. So in the end, you say I can approximate my summation over all possible paths by one single placeholder path, which is the semi-classical trajectory, the ones that we observe in Newtonian mechanics. And if you go to I think it comes from quantum chromodynamics, where this is equally important for transitions between rare things and tunneling and all these kinds of things, where then they are called instantons. If you have a double well, then this instantaneously bridges from one of these states to the other. Okay, so this is the whole setup. In the end, what needs to be solved is again an optimization problem. I'm given a functional, and I want to find the minimizer of this function. So in general, maybe that's it. If you know numerical optimization, then you can just do it. If I give you an STE, you can explicitly write down S, I did that, and then you just minimize. And that's done in practice. But there are special cases where there is more possible and where you can write it down a bit more explicitly. And I wanted to discuss before the break one of these special cases. The special case that I mean is what can be called the reversible case. We're now entering statistical mechanics or statistical physics theory, where you would say all of these SDEs defining some random system, and some of these random systems have certain properties like time reversibility, detailed balance, and these kind of things. From the perspective of a stochastic analyst, the reversible case simply amounts to the existence of a potential. So U goes from RD into R, and then our SDE is a gradient flow in this potential. Vector 2 is just convention. So this is the special case of what we had before, where this was an arbitrary vector field B. Now this is no longer an arbitrary vector field, but instead I guess a conservative vector field, where I have an underlying potential where I'm just sliding downhill. I have a landscape, and my X always wants to go to minimal U, and the noise drives me out of minimal U or perturbs me. This is a special case because if you go ahead and write down the Fokker-Planck equation of that, you can explicitly solve it, and you know that the invariant measure of this process has this form. You will recognize a bit of a parallel here, is that this potential energy also gives you the exponential scaling of your probability distribution. That's just a normalization factor. So this is Gibbs measure. And you might think that this is a comparably restrictive case, but there are lots of applications in reality that fall into this class, maybe the largest being molecular dynamics, where X would be a large number of positions and velocities of particles, which interact in a certain way, but the dynamics are conservative so that you can describe the evolution of maybe a tiny volume of water or maybe some protein that tries to fold itself or so on in terms of this equation where D is maybe 10 to the 5. And then you do know the Gibbs measure, but you're still interested in sampling, and in particular you're interested in conformational changes of your molecules, which will behave according to this one in the low temperature limit. So epsilon takes the role of an inverse temperature. Sorry, over temperature. In any case, the intuitive image would be that U has some kind of contour lines, and then you would expect your dynamics to somehow zero in on the local minima of this, but then your noise driving you out of this so that you have a cloud around here, and the shape of the cloud is exactly the one that's given by your U. Why is this case nice? It's because the large deviation rate function, or the action of the process that corresponds to it, is very easy to simplify. Imagine we have the question of how likely is it to go in the low temperature limit from this point A to this point B, down here. The thing that we need to minimize is this, where I now say this is phi dot, and because B is minus gradient U, I have a plus gradient U here. There is an obvious minimizer for that, and that is phi dot equals minus gradient U of phi. Phi dot is minus gradient U of phi. This is just 0. You cannot be lower than 0 for this integral, right? This was true in general. This is not restricted to the reversible case. You could have phi dot equals B. It's also 0 actually. I just want to make this case because there will be a second case that cannot be treated in the other case. But what I'm saying here is that if there exists a path from my point A to my point B that I'm interested in, for which there is a realization that's just sliding downhill with my dynamics. I wouldn't even need my noise. This is the case where the noise is just 0. In the limit epsilon to 0, this is of course the path that you select. If I can deterministically go anyways, if I don't need the noise, then in the case noise to 0, this is the thing that will definitely happen. It's maybe even trivial, right? If I take the limit of epsilon to 0, then I just have a deterministic equation. That solution is this. Okay. In some sense, this action description is a variational form of writing down the ODE in the first place. And then the minimizer is the solution. But there is the other case for which we need the noise. If we now want to go from B to C, uphill, you could call it, right? This is some kind of hole or valley that you move down into. But now we want to go from a lower point to an upper point, meaning there is no such path, which just follows the dynamics. I need the noise. And that's the case where we are usually in, and that's the case where this all becomes interesting, of course, because what I'm saying is, what's the limiting pathway as I let my noise go to 0? Obviously, there is no path if the noise is equal to 0 because you need the noise to move uphill. So this is as the noise becomes smaller and smaller, but still finitely big or non-zero. How would it work? This is maybe A to B. In this other case, I make the following trick. This is just the action itself. And then I say, I just want to flip the sign here. Phi dot minus gradient u. That's of course something else, so I need to correct. And the correction factor is 4 times the mixture term, right? It's just, I guess, I don't know the English term, these binomial formulas, right? So the thing that is missing here is phi dot product with gradient u phi dt. Factor 2 because 4 times. This is phi dot squared plus 2 mixture term plus gradient u squared. This is phi dot minus twice the mixture term plus this squared. So the thing that I need to correct for if I replace this by this is 4 times the mixture, right? And now if you have taken any multivariate calculus or like geometry and motion type module in your life, you will recognize that this is a line integral. I'm saying dt, but I have a phi dot times the gradient of something. Or maybe if I write this more intuitively, what's written here is this is a du by d phi, this is a d phi by dt, and then I have a dt. So a d if you want, right? d phi dt. But all I'm saying is I go along a trajectory phi, and I integrate up the gradient of the potential, means that all that this right an integral evaluates to. So the first one I got to copy. Is twice u at phi at the end minus u at phi at the beginning. Maybe fundamental theorem of calculus. So I'm integrating the gradient of a potential along a curve is the same as just evaluating the potential at the end. So what you will notice here is that all of this just depends on the endpoints. We call this one B and this one C. Sorry, this one C and this one B. But any phi that I choose, these points will be the same, right? Regardless of which path I take, this portion of the integral is constant. It's the potential at the end minus the potential at the beginning. No way of changing that. It's some constant. So what I can now do is I am free to choose whatever phi I like in order to minimize the first part, because I have no control over that one. This will always remain. The phi that minimizes this part turns out to be phi equals gradient u. This is not the same as this one. This is plus gradient u. This was minus gradient. If I choose phi dot equals plus gradient u, this one becomes 0. And the whole answer is just u at the end minus u at the beginning. Twice. The factor 2, I mean, might be different depending on your special definition, but it doesn't matter. What matters is if we choose this path, it will just be depending on the difference of potential between beginning and end point. So why is this remarkable? This says, if there is the possibility of reaching my endpoint deterministically, I'm just going to slide downhill deterministically. If not, what I'm doing is the same thing, just reversed. I'm going uphill exactly the way that I would slide downhill in opposite direction. It's time reversed, the same thing. So what this is saying is that, and maybe that makes clear why this is called reversible, the reversible case. Either I do what I would deterministically do anyway, or I do the time reverse thing if I can't do the forward thing. Or another way of phrasing is the probability of going from A to B, sorry, the way that you go from A to B and the way that you go from B to A looks the same. The probability is not the same, but they look the same. Just time reversed. And you can now make like one additional step to get the detailed balance condition out of this, but this is kind of like the variational argument on why the detailed balance condition holds for these kind of gradients. Detailed balance condition being the probability of being here and going to there must be the same as the probability of being there and going to here. Because the probabilities also scale with u. This is the case. All right. So this is an extremely nice case because we can basically write down explicitly how these minimizers must look like. You're either going downhill or you're going time reverse downhill. Any transition path does y dot equals minus gradient u or phi dot equals gradient u. In particular, if you consider a case like, sorry, that's I'm crossing too many. I have two minima, such as in the ship capsize example. I have two fixed points. The ship capsize example wasn't gradient. But I have two stable fixed points, and I ask how likely is it that my system changes from here to there? This would be a protein folding case where this is one configuration of the protein, that's the other one. Both of them are local minima in the very high dimension energy landscape. What you will do for transitioning from here to here is uphill. You're going exactly the same path as you would go downhill coming from here, and then here you would just go downhill the usual way. That is the most likely transition pathway going from this point to that point. And you will always go, so this, the isoline that I'm drawing here is somehow a contour of the potential landscape. This is one valley, this is another valley. So this one here corresponds to something like a mountain pass. This is the point of lowest potential between that and that region. And that's maybe intuitive. If you really interpret U as some kind of landscape, I want to go from one valley to the other. The cheapest way of doing so is not going over the mountains, it's going through the lowest valley between the two. So a transition path from one minimum to the other always goes through the saddle point in between. And if there's multiple, then it goes through the saddle point with lowest potential energy. The relevant saddle. So I suppose what happens next is how do you actually numerically compute this? And I want to show this, but maybe we do that after the break. But one quick thing that I want to show with my broken discipline laptop is let me wiggle once, and if it doesn't work, you just have to live with it. It's better, huh? No, we do that. Okay, you have to live with it. It's the following situation. This is a Lennard-Jones mixture. I have particles of different sizes that interact between themselves with the Lennard-Jones potential, which maybe you've come across, maybe not. This is just a force between two particles that's attractive on large scales but repulsive on small scales so that they don't overlap at the same point. It's a lot of particles, and they each interact with every other one at the same time. But the whole dynamics is a gradient flow, because the interaction dynamics just give me a conservative force, energy is conserved, and so on. The question that I can ask is, what's the most likely way of exchanging the positions of the green and the red particle? Because the configuration that we are currently in is one local minimum. There are many local minima of different arrangements of these particles, but I can compute this kind of trajectory between this local minimum and the local minimum of these two exchange, which also must be one because kind of like topologically it looks the same. And the video gives you this path. This is one of these paths exactly, just in this extremely high dimensional space and then visualized as the position of the particle. But this is exactly what people do in molecular dynamics and so on to compute how would such a transition happen. So this was a transition through many, many local minima, through many, many cells, and so on, but I'm always aligned either uphill or downhill, and the way that this was computed, I wanted to show you next. All right, so see you after the break, maybe 10 past. All right. So let's start again. So the last thing that I told you is in the simple case of a gradient flow, or simpler case, these can still be rather complex problems, we can explicitly compute the most likely transition trajectory between any 2 points, why either simply follow the deterministic dynamics downhill, or to do exactly the time reversed thing and going uphill in exactly the opposite direction. The consequence of this is basically summarizable as phi dot is parallel to gradient. Gradient U gives me a vector field everywhere, and if I want to connect 2 points, I need to find a trajectory that's parallel to this everywhere. Maybe not considering so much what's the exact parameterization of that, just saying that the direction is always parallel to the flow. So what I now wanted to do is to give me an algorithm that computes exactly such a thing. And I guess in Hamiltonian dynamics, these kinds of trajectories are known as heteroclinic connections. Fancy word, maybe heteroclinic connection. If you're connecting a fixed point to a saddle point and then the saddle point to a fixed point, you have not between arbitrary points, but usually you would start or end or both at a fixed point. And the method to compute a phi that has this property is called the string method. It has nothing to do with string theory. But what you want to find is a phi of arbitrary parameterization. So in this case, we are saying we want a phi from 0 to 1, ignoring the temporal aspect of it. It's just like this is just the trajectory itself into our space here, RD. This was RD here, right? All of this is in RD. With the property that clearly phi of 0 is supposed to be our initial point, and I call it A maybe. Phi at the end, which is now 1, equal to E, and phi dot parallel to gradient U elsewhere. And the simple way that this algorithm works is take some initial guess phi k of S. So S is in 0, 1. And then do the following. First, evolve the whole phi k according to the gradient dynamics. Phi k is phi k minus 1 at S minus, forward Euler if you want, delta t gradient u at phi k minus 1 at S. So there is no magic here. Numerically, I would say this is a whole trajectory, meaning I discretize this trajectory numerically, of course. It's a collection of points in my system. Maybe it's this point and that 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 point. Of course, this would not be my initial guess, that's my final result. But I basically discretize all of these. Maybe I start with something that goes from here to here. And then the first step simply says each of these points individually flows with the gradient flow. So I'm trying to go always downhill. So I should be perpendicular to my contour lines. This is how they would evolve, and this is how the points are located after step 1. Clearly, what they should do is a portion of them should eventually collect in this point, and the other portion should collect in that point. But they are connected. They don't feel their connection at this moment, but this is exactly step 2. Reparameterize phi by arc length. I guess differential geometric term, but what I mean is I have now a new trajectory, but the points are not equally distributed. I just redistribute my points along this trajectory with equal distance. So phi dot shall be a constant. Or in discretized terms, phi at Si minus phi at Si minus 1 shall be some kind of constant. I want their distance, some more. I want their distances to be equal. And then maybe this is intuitive. What shall happen is that the endpoints eventually will fall down into because they are unconstrained, fall down into the stable fixed points, but all the way, the whole trajectory is spanned between them. And because I always redistribute points, they will not clump up at the minima, but they will have a nice distribution of points along the whole transition trajectory. And what I will eventually converge to is exactly this point, where the point at which I cross the separatrix will be exactly the saddle, because that's the point that I flow to if I would restrict myself to that submanifold. This is an extremely easy algorithm. You might maybe think, how do I exactly do the reparameterization? But all that I need to compute is something like the length function, right? 0 to t phi dot of SDS. This is the distribution of the points along it, and then I need to reinterpret it with some interpolation, maybe linear or so, to put the points equally spaced again. While this one is simply applying the original gradient flow that I started with to every image along the transition trajectory. If I already have a code, maybe a really fat molecular dynamics code that takes a fine integrates forward, I can implement that as well. I just need like 100 copies of my system, and I push each of them forward as well. And then I just equally space them, I'm done. This is why this is used indeed in large-scale systems, and that's also why I could do it for the Lennard-Jones mixture. All I needed to have is a code that integrates the original dynamics of my Lennard-Jones mixture and reparameterize. So that's the thing that I wanted to implement on the noisy screen. So let's see how far we get. Sorry, so the other days wiggling helped, and that has stopped by now. But I have a very big font, so hopefully that's it. So this is MATLAB again, and I've chosen a certain potential that I will just write down. So V is 1/4 1 minus x squared squared. This is a double well, maybe you've seen that. Plus 0.25 times y times y minus cosine pi times x plus a half. So it's just a choice because it looks nice. So I would do, just to show you, 100 points minus 2 to 2. How that looks like. How do I call this one? Does that work? The contour plot of this x versus y versus v of x. Y. Some number. Am I doing correctly? 0.25 1 minus x squared is y dot times. This is the potential. So I have two minima, but I have perturbed. So this is the double, well, basically in x, and then in y I perturbed it a bit with cosine or whatever. But you see that there is a minimum here, and there is a minimum here. And I want to compute the path that connects this point to that point with this string. So I want to implement this string method. So maybe the first thing to do is get an initial guess. Maybe I say x is the lim space from 1 because, yeah, so how many points do we take? Maybe 100. And y is just zeros. Is that the same size? So I have x and y. So if I would plot this into that, so plot x, y in white, that this is the initial path. So something like I hinted at there. Maybe with the points, there's 100 points on that line. I could do fewer, but let's do 100. So I would now say I need a number of iterations, maybe also 100. And dt, I always pick 0.1, and then I say, as a function of iterations, I need to push forward the x and the y. So dx and dy are something, and for that I need the gradient of the potential, which I will just copy from my notes because I don't want to do the gradient of that thing now. And I hope that I do everything right. So this is minus x times 1 minus x squared plus 5 times pi times y times sine pi x plus 0.5. I just wanted to pick a non-trivial potential, and this is why the computation of the derivatives is a bit odd. You can check whether I did it right. Hopefully we will see. Sine pi x plus 0.5, and then I need dv by dy. It's also a function of x and y. Is 1/2 times y minus 1/4 times cosine pi x plus 0.5. So I would then say, if I just evolve them, dx is dv by dx of xy. dv by dy is also that. So I'm doing it in this split way because I don't want to update x first and then y. Then the y update would also have the updated x already. And if I now go ahead and say x is just x plus dx and y is y plus dy, they should already evolve. Maybe I should plot them then. Contour plot, and then I hold and plot x, y in white. That's a line. I need to do minus gradient. They were going up. So now all of the particles are sliding downhill. They should eventually collect in the minima. But you see also that their spacing becomes bigger and bigger. You can already tell that this looks a bit like the transition path. Maybe you would intuit it, but the points eventually will slide down completely. It's so slow because I forgot to over here, so it's overlapping a lot of. Is that visible despite the noise? Yeah, I think so, right?
Yeah.
So the only thing that is missing is the reparameterization, and that's maybe also the hardest step. So what I would do here is I need to compute this L of t function. Is this the integral of the norm of phi dot? So what's phi dot? Is diff is just a finite difference. Diff of x squared plus diff of y squared, and then the square root of that. This is the norm of the finite difference of my path at every point. This is a vector, so I need the cumulative sum of that vector. What's cumulative sum? I'm just saying if A is this vector, then cumulative sum of A is the first entry is the sum of all entries before that. So this is 3 because it's 1 plus 2. This is 6 because it's 1 plus 2 plus 3. This is 10 because it's 1 plus 2 plus 3 plus 4, and so on. So this is just the integral up to every point in the thing. And because diff is a central finite difference, it has one fewer entries, so the first entry will be 0. I think that should work. Let me check. Call that t. Does it make sense? So it just might be that one of them is the wrong size. This one 0 times x. That's good. So this is basically the length of the trajectory. The first point is located at distance 0. The next point is located at distance 0.0041, and then 0.0. That's basically the distances between the points. The distance from the initial point to the first, to the second, to the third, and so on, all summed up. And then all I need to do is to reinterpolate. So x becomes the interpolation of the points are located at t, they are valued x, and I want them to be equally spaced between 0 and 1. I think that should go. This interp 1 is linear interpolation. So all that is saying is that interp takes the locations of points and the values at the points and interpolates them to new locations. This is the array that determines where they are located along this string, and this is where I want them to be located along the string. So let's see whether that's it. It's not. I see what I did wrong. T is not going from 0 to 1. T is up to a bigger number. So I want to normalize it t by t end. Now t is between 0 and 1, and I want to interpolate. So now every iteration, you don't need to do it that often, but it may be the easiest to implement. I redistribute the points along the string with equal space. So what I did here is discretize this integral, and then I just redistributed the points according to equally spaced instead of the spacing that they actually have. And you see that after a few iterations, we converge to a string of that type. Maybe we should give it more iterations, but it will eventually slide down. Maybe it was already, I'm not sure how much still changed after 100 iterations.
Why is it not symmetric?
The whole potential is not symmetric, but it's still a question of what exactly is happening here. So I think this is maybe the better view. You need to rescale the axis in the proper way to see that this is always perpendicular to the contour lines. If I rescale the axis, this looks a bit odd. What do you mean symmetric? Left-right symmetric?
Yeah, like
the potential is.
Yeah, I don't have the potential in mind anymore, but it's not.
Well, it's a weird potential. I mean, it's just like I perturbed it on purpose for it to not be like a nice.
Yeah.
And you can tell a bit that maybe you can't tell. It is not symmetric. All right, so this is the string method, and as I said, because if I don't struggle too much implementing it during a lecture, this is doable for very complex systems, right? You just have to compute these distance vectors. Maybe there's a question of if you're in a high-dimensional space, what norm do you take? I just took a Euclidean. You're free to take any norm, but these are maybe higher-level questions. What I'm saying is just I integrate every single point along the trajectory. Maybe I could get away with far fewer, in fact. And then just reparameterize. All right, so this was the reversible case. And let us now try to go on to the general case, where there's much less that can be specifically said. So the general case, I can basically name the simple recipe, and that's called the minimum action method in the literature. But of course, we have already established that all that we need to do is to minimize the action. So naming the method like that is maybe over-descriptive even, or non-restrictive. Just to remind you, we're interested in finding the minimizer of the action, but only minimizing over those trajectories that do what we want. Like so. And now, not sure how many of you have done any calculus or variation classes, but maybe some of you are physicists and have at least seen classical mechanics. Obviously, at the minimum, the derivative of this thing must vanish. That's how you would find the minimum in school. You're given a function, you compute its derivative and set it equal to 0. It's a bit more complicated here because it's not a function, not even a RD function, but it's a functional. So it maps from a trajectory to the reals. But it's still the same thing, just that these look even more weird. This is like the variational derivative now, s with respect to phi. Should be 0. That's the only equation that we need to solve. And for an s that is given by the integral of a Lagrangian density, this is a well-known thing from classical mechanics. It's simply the Euler Lagrange equation. So the s by d phi is the partial derivative of the L by d phi minus d by dt, the L by d phi dot. This is what you would do in Hamiltonian mechanics as well. So the minimum action method, and I'm not going to spend too much time on this, is basically computing this equation concretely for the L that we have. For SDEs, we know the L precisely, and we can compute these quantities. And then just doing a gradient descent in path space with this gradient until the gradient is 0. Or maybe something more sophisticated, some quasi-Newton method, some conjugate gradients, or whatever minimization problem you fancy to minimize the action. That's why it's called the minimum action method. You take the action and you minimize it with numerical optimization. Solve via gradient descent. Computationally, this is more complex than what we did there, because what you need to do here is to compute higher derivatives of your right-hand side. The only thing we needed there was the dynamics themselves. What we need here are derivatives of the dynamics. I mean, I need the derivative of the potential, but that's the dynamics itself is already the derivative of the potential. Right? So if this would be for a potential flow, you would have gradient V in this equation, particularly this part. So that's all fine and good, but there is another way of viewing this, and I promised this to a few physics people, I forgot who it was, is that whenever we have an action that's an integral of a Lagrangian density, or a Hamiltonian principle such as this, where you're saying the variation of the action is equal to 0, you can invoke classical mechanics. And that's what I want to do. You can transform this into a Hamiltonian system and solve that instead. And these are in some sense very abstract Hamilton's equations. The energy that's given by the Hamiltonian has nothing to do with the energy of your system. The conjugate momentum has nothing to do with any momentum of the physics that is described by this system. So in classical mechanics, we define a so-called conjugate momentum as partial derivative of the Lagrangian with respect to the time derivative. So if I start Greek letters for the fields, then I need to use Greek letters for the conjugate momentums. Maybe x and p is what you use in classical mechanics. I use final theta. And the Hamiltonian which in its most general form, which maybe was not, I mean, who here had classical mechanics? I have quite a few. Yeah. In its most general form, is defined as the differential Legendre transform of the Lagrangian. I will write that down. So the Hamiltonian, which is now a function of the field variable and the conjugate momentum, is the supremum over phi dot dot theta minus the Lagrangian phi dot. If L is convex, this can be written down in a more specific form, but the Lagranges that we are dealing with here can be fairly general and more general than maybe in quantum mechanics or classical mechanics. If I have this Hamiltonian, I have to write this down. This is the Legendre transform of Legendre because of the supremum thing. Then the minimization problem this one amounts to solving Hamilton's equation. Phi dot equals dh by d theta. Theta dot equals minus dh by d phi. This is a completely equivalent formulation of the problem. You're increasing your space by a factor 2 because you now have a trajectory in phi and also in theta, but you're reducing your derivatives by 1. It's maybe in some sense analogous to transforming a second order differential equation into two first order differential equations, but slightly different transformation at that time. I have now two equations that I can write down that I can solve, and if I find a solution to this set of equations, I have also solved the minimization. But for the SDE that we started with, we have a concrete Lagrangian. So how does it look concretely? Here, Lagrangian was 1/2 phi dot minus p of phi squared. So the conjugate momentum dl by d phi dot simply phi dot minus d phi. And it is in this sense that you can somehow interpret the conjugate momentum as the optimal noise. You're now solving for the field variable and the corresponding optimal noise variable. If I have this theta, then I can say h of phi theta, without doing the full Legendre transform, is not necessary in this case. Theta times phi dot minus L of phi dot. Theta times phi dot minus 1/2 phi dot minus b squared, which is exactly theta squared. And phi dot, I just want to transform it to phi and theta and reduce all the phi dot. This also means that phi dot is equal to b plus theta. So phi dot is b plus theta, so I get a theta times b. And I get a theta squared minus 1/2 theta squared is plus 1/2 theta squared. This is the Hamiltonian. Theta times b plus 1/2 theta squared. This might be completely meaningless to you, and that's fine, I guess. There is some secret sauce in here, namely that this square comes from that we originally had a Gaussian probability density, and Gaussians are always associated with squares in the exponent. If you had other distributions like alpha stable Levy noise, also this square would be replaced by an alpha maybe. If you have completely fancy noise like Poisson type or so, this wouldn't be squared. The dependence on the conjugate momentum, but still convex. So if we have this Hamiltonian, then phi dot being dh by d theta is equal to d of phi plus theta, which we already knew. And theta dot minus dh by d phi is equal to, so I need to compute the phi derivative. The only thing that's dependent on phi is this one. So it's something like gradient b of phi transpose, if you think about it, this is high dimensional, times theta. Exactly. Minus. So these are the equations that we would need to solve instead. One thing of note here is that phi dot equals b plus theta is basically the original equation. Just that instead of a noise here, I have a theta. Not only is this somehow neat in letting us interpret what the theta even means, but also if I have a code to solve my original equation, I can use that code to integrate this equation instead. This is the same. I mean, B is where all the secrets is in, right? And this is where the molecular dynamics or the climate or whatever code is located. The theta equation is basically a linearization of the original equation around phi. This is gradient phi, gradient b at phi. The only thing that needs discussion is the boundary conditions of phi, because in the original problem, you would then have phi of 0 equals a, phi of t equals b. And that is awkward. I have one equation with two boundary conditions, one at the beginning and one at the end, and one equation without any boundary conditions. So this is where I need to hand wave even more. Maybe you have seen that hand waving. I can transform the boundary conditions. I want to integrate the forward equation, the phi equation, forward in time starting at a, at my initial point. But how can I do that and guarantee that I end up at b? This is very hard to do. So instead, I introduce a Lagrange multiplier to enforce this final constraint. So I would, maybe you've seen that. Yeah, you probably have also, I don't know. I transform my Lagrange into this one. So that's the same as before. And then I introduce an additional term that enforces my constraint. So maybe I don't want to end up at b. I am back to the original extreme event case where I want some observable at the final point to have a certain threshold value z. Even worse, right? How would you ever enforce that final condition? So instead I enforce it with Lagrange multiplier, saying that there is a lambda such that f of phi of t equals to z, and then I can go through the whole motion again. And what I end up with is the same equations as before. Phi dot is equal to b of phi plus theta. Theta dot equals to minus gradient b of phi transpose theta. But I have phi of 0 equals my initial point, and I get a final condition for theta. Theta of t is equal to lambda gradient f of phi of t. This comes from the variation of this with respect to phi, which enters then this equation. So this I don't want to go through this completely because it's already explained. This is a much less awkward system to deal with, because I can simply integrate this equation forward, starting at the initial point. That's very close to the original system that we had already. And once I've done that, I can integrate this equation backwards in time, starting with this final condition that comes from phi. Of course, I need both equations to match, so I would do that iteratively. This forward, then using that to insert here, this backward, and using that to insert here, this forward again until convergence. This is how you would solve this. The intuition here is maybe that this is just what your unknowns do for the noise realization of theta, and then theta somehow needs to be backpropagated in order to somehow get the causality right on, if I want this final condition, then what should it have done in the past in order to reach that. So this is the last thing that I want to implement, solving these Hamilton's equations on the noisy screen. So maybe the equation that we are integrating shall be sampled first. I want to do a b that's just minus x. So this is an Ornstein-Uhlenbeck process. Maybe 100 time steps, maybe dt 0.1. I take a specific epsilon because I've tested the how realistic it is to measure them. And maybe I take, similar to the Monte Carlo example, 10 to the 5 samples. So this is very similar to the codes that we did on Tuesday. X is just m realizations, and the trajectories themselves are with an nt. And then I say the step going from 1 to nt. I'm just integrating the equation for now. X is equal to x plus delta t times b of x plus square root of epsilon times delta t times a random number. This is the SDE. Did I call it sampling? Did I do a mistake? Did I call it sampling? Yeah, that's 100,000 random variables, random realizations. Gaussian around 0, that's what you would expect. So let's record the trajectories. This is too many of them, of course. 100,000 I can't plot. But how many do exceed the threshold? It's just a handful. That's why I chose this epsilon and this n. If I have 100,000 trajectories, then 19 of them exceed the threshold of 1. Maybe I can try to plot them. Only those where the final point exceeds z. So you see they are doing their thing, but then at the end, they are creeping up to the final point that's equal to 1. And maybe one thing that we can do then is, and that's what I did in the Monday lecture, on top of that, I can compute their mean. They are fluctuating around something here, right? They're all doing a similar thing. The width of that tube is somehow related to epsilon, but I cannot afford a smaller epsilon because then even fewer trajectories would do what I want. So I'm averaging all those that hit the threshold. Plot that in red. That's the average extreme event. Starts around at 0, but at some point it decides that it starts needing to go upwards, and that's what it does. So maybe that's what we want to compare against, because now the goal, of course, is the solution of these Hamilton's equations should approximate this red curve. And I would be able to completely skip all kinds of sampling. I did 100,000 experiments here. It always looks fast, but if you are talking about serious systems, this is not easy to do. And the average way of realizing this extreme event should then be described by this phi as well. So let's call this instanton. I again have 100 grid points. So what do I need to do? Maybe a number of iterations, 100. and over these iterations, I have an x and a p, that's phi and theta, which are both trajectories, so they are nt sized. What kind of final condition does my theta need? Lambda times gradient f. In this case, f is just the identity because I want a large event, so I pick f of x to be x itself. I want x to be large, so the observable is the random variable itself. I don't need to do any mapping. I'm in 1D anyway, so there's not kind of much mapping that I need to do. So the only thing that I need is that the final p is equal to lambda, and I need a lambda. And you see here a problem cropping up that's maybe not obvious. There is a Lagrange multiplier associated to each endpoint, and you can compute like some adaptive thing that tries different lambdas and then chooses the right one. I did that at home, and I know a lambda that's the right one, 2.1. But you can, for example, dynamically adjust the lambda to get the final z. Because I can't prescribe the final z, instead I prescribe the lambda to get a final z. So we set the final p to some lambda, and then I need to integrate backwards in time the p equation. So I say p at s is p at s plus 1 plus dt times, so p is minus x, gradient b is minus 1. I always write 0 times x minus 1 because then it's the right size. dt times gradient b transpose, we're in 1D, there's no transpose, times p. That's the old equation. Plus instead of minus, because I'm integrating in backwards direction. And then forward. 2 to nt. X at s is x at s minus 1 plus dt times b of x plus p. I think that should be it. If I now go ahead and plot x, hopefully that works already. What is he complaining about? dv of x, of x, it needs to be of x at the right time. It's not going to be the only mistake, I think. Yeah, and there you go. Quickly converge to something. You didn't even see it converge, or maybe you did, I'm not sure. Can you tell it? No, it's so quick after a few iterations already to converge to the right thing. This is a trajectory that starts at 0 and ends close to 1 because of my smart choice of lambda. If I would have picked a different lambda, I would just pick a different endpoint, 0.5. And you can see that you can somehow adjust it. Often this is not a problem because often you want to compute the instantons for every possible endpoint. So sweeping through z or sweeping through lambda is the same thing. But now that I want to compare against a specific case, I need to use the right lambda against it. So this is the instanton. Maybe let me do the sampling again. And then what did I plot? I plotted this and the mean. Now I want to compute the instanton without, oh, sorry, plot this and the mean. It's a bit ugly, but that's just it. And then I compare against the instanton. So I plot the instanton in black dashed. And that's what I wanted to show, right? So the black curve very neatly approximates the average extreme event. If I would have computational power to collect many more examples, I could have afforded an even smaller epsilon. Actually, the epsilon is not very small, right? The fluctuations are quite big. The smaller the epsilon, the more the blue cloud around the most likely trajectory will converge to the most likely trajectory itself, which is the black box. But it already works for this epsilon if you look at the average, right? You can basically tell this is what all trajectories need to do in order to realize this final event. So because this is such a simple system, there's not that much to look at, but it's basically at what point in time do I need to start ramping up from the zero? That depends, of course, a bit on the drift. But if you had a higher dimensional system with more complicated dynamics, there's much more things that you could do in a correct or in an incorrect manner, where then the sampling would actually give you a transition tube, and then the Hamilton's equations, which are not so difficult to implement, give you the main point. Maybe the last point is that, yes, in order to compute the Hamilton dynamics, I needed to compute the derivative of the drift, which I didn't need to do for the string method. It's misleading maybe because I had the derivative of the potential, but that's B itself, right? All right, so this was it. This was a very short overview of our large deviation theory, in particular sample path large deviations and how to compute them. And thank you for your attention.